Hello everyone, welcome to today's webinar all about Spark and the Typesafe Reactive Platform. My name is Laura Masterson, I'm the Community Manager here at Typesafe, and I'm excited to welcome Dean Wampler, a consultant here at Typesafe and our resident big data expert. He's going to be walking us through how Apache Spark and the Typesafe Reactive Platform will be working together. Before I hand things over to Dean, I just wanted to make a few announcements. First off, this webinar is going to be recorded, so if you miss any part of the presentation or if you're having audio difficulties, you'll be able to watch the remaining part online shortly. We'll also be sharing the slides, so if you want to browse through those as well, you can do so. Also, if you have questions throughout the presentation, feel free to insert those into the little chat box in the lower left-hand side of your screen. Dean and I will try to answer any questions as we go, saving a few at the end for Q&A. I think that's about it in terms of announcements. If you have any questions, just let me know. Dean, I'm going to hand the floor over to you. Thanks so much for joining us.
All right, hello everyone, and thanks for dialing in. So we're going to talk today about the new tool that's been emerging as a sort of the successor of MapReduce. It's called Spark, and we'll also talk about how it interoperates with the Typesafe Reactive Platform. So just a brief history of big data and how we got to where we are today. The internet basically created petabyte data sets. Well, it may be that the NSA had them already, but nevertheless, the ones we know about were created over the last 20 years or so as companies like Google and Yahoo, eBay, Twitter, and so forth wrestled with unprecedentedly large data sets that just did not, they just weren't manageable with traditional tools like relational databases and so forth. So that kicked off quite a bit of innovation to invent new tools for dealing with these data sets. And some of those tools include Hadoop, which is basically a clean room re-engineering of a Google project called MapReduce, which is a compute engine. We'll talk a little bit about that in a second. And a distributed file system, which is the third bullet point, that we needed essentially virtualized file systems on massive scale. We're talking petabytes in size. And that also required a lot of innovation to make them resilient against hardware failures and so forth. And also, NoSQL databases emerged out of this movement as we realized that maybe we needed to relax the relational model, relax the idea of transactional operations in order to improve availability and deal with network partitions in the internet and then deal with the repercussions thereof. But also just to be able to manage all this data at very large scale, but at very low cost as well, relatively speaking. So if you look at a traditional Hadoop cluster, it looks something like this. On the left-hand side, the sort of circular bubbles are the user submitting jobs written in MapReduce or written in Spark. We'll see that Spark is essentially a superset of functionality that MapReduce provides. Those are submitted to some sort of master resource manager. That resource manager then breaks down the job into various tasks. These are typically individual JVM processes, and they're distributed to slave nodes around the cluster. Of course, I'm only showing 2 nodes here, but it could be even thousands of nodes. And typically, these tasks are run on the boxes that actually have the data that you're asking to process. And that data is managed in HDFS, the Hadoop Distributed File System, with a master process called the name node that knows where everything is in the cluster. And then on each node, there's a data node that knows specifically what blocks of these large files that it has. And then there's just a lot of disks in these systems where all this data is kept. So that's typically how a MapReduce job or a Spark job is submitted in a Hadoop cluster. This would be batch mode processing, where I've got all this data parked here and I want to do some global analytics over it, some massive query or so forth. And there have been tools written on top of MapReduce and Spark that give you SQL abstractions, data flow abstractions, and so forth. And in a real environment, you have to get data in and out of these systems. So I'm also showing here that you might be ingesting log data through Flume, which is a service for this purpose invented at Facebook. There's a tool called Scoop for interoperating with databases, not only relational databases, but even NoSQL databases. So you might periodically pull data out of your transactional database into Hadoop for offload analysis. And Kafka is a messaging queue system with great scale properties that might be used for other purposes of ingesting data that's coming in that needs to be handled reliably. So that's kind of the traditional picture that if you know anything about Hadoop, this will look very familiar. Hadoop is often used for data warehousing and other offline purposes. It has been used to some degree for online transactional work, such as embedding a database called HBase on top of the cluster. But there's a lot of properties about Hadoop that make that a difficult proposition, and some of those we're going to talk about a little bit here. We won't talk much about the file system and its strengths and limitations, but mainly we want to focus on this compute engine called MapReduce. And it's had a number of limitations that have just grown increasingly concerning or limiting as time has progressed. And they include a rather difficult programming model. Even though it is general purpose and can be used to implement most algorithms, it's actually not that flexible, and it requires a lot of specialized expertise to implement non-trivial algorithms in this model. And the API in the Hadoop MapReduce case is particularly onerous to work with. It's very low level. It's full of details that you have to manage yourself that it doesn't handle for you. And so it's actually non-trivial even to write relatively simple algorithms. It also has rather poor performance, especially over complex jobs. Now, you might think that if you're building a big cluster, then performance would be very important. But basically what has happened is it's compromised for local performance problems with just massive concurrency, massive parallelism actually, to kind of compensate for it. But nevertheless, it's been an issue, especially when you're getting to scenarios like the last one here, where we want to be able to handle events in real time. We want to be able to let people query the data interactively, and that becomes difficult if you have poor performance at sort of a local scale. And to be specific about one of the performance issues, a lot of times to write a MapReduce job, you actually sequence together several steps of mapping and reducing, mapping and reducing. And between each of those jobs in that sequence, MapReduce has to flush all the data back to disk, even if it has terabytes of data into memory. And then the next job will read all that data back into memory. So it's a huge performance penalty when you run into that scenario. Two other issues that we have to deal with are the following. I can click this. There we go. It's actually somewhat inflexible for algorithms that are easier to implement as iterative algorithms, where I'm just, say, testing a solution, finding the errors, tweaking it, recalculating it. A lot of machine learning algorithms actually work this way. It's also somewhat difficult to implement graph traversal algorithms, which also tend to be small steps after small steps after small steps. So these are limitations that people have invented various hacks to work around, but it's still a barrier. And finally, it doesn't really scale down that well. It's fine for really large data sets. In fact, it's the only game in town for extremely large data sets in Facebook size. But if I want to run it on my laptop, it's rather tedious to do. If I actually have a very small, relatively speaking, data set, and I just need maybe a cluster of 5 machines, it's just not that easy to use Hadoop and MapReduce in particular for such small data sets. And so we'd like a better solution that scales from very small work up to extremely large scenarios. So what are we going to do about this? Well, for the last few years, there's been a project at Berkeley called Spark. It started as a grad student project and gradually got more and more sophisticated, more and more capable, and now it's a top-level Apache project. And Spark actually addressed all of these problems very nicely. First of all, it has a very flexible, composable programming model. And what I mean by that, and we'll come back to it a little bit more in a few minutes, but just to give you a sense of what this is, instead of having just a very coarse-grained map step and reduce step that you have with MapReduce, you have much more fine-grained operations that you can perform that are built right into the system, like mapping and reducing, but also filtering, folding, and so forth. And these compose beautifully to build up arbitrarily complex applications with relatively little effort. In fact, as we'll see in a minute, the API is very concise and powerful, so you can write actually typically script-sized programs, just tiny things that do incredibly difficult stuff. So it's a huge win for developer productivity, as well as expressing the problem that you need to express. It also has very good performance. So that issue I mentioned about flushing data to disk and then reading it back in, Spark has a very intelligent caching model, so it will cache data between processing steps and largely avoid that disk I/O overhead. In fact, that fact alone sometimes contributes an order of 100, a factor of 100 improvement over MapReduce jobs. And another issue that's very important for us is that now we need to be able to react to events as they happen. So just to give you an example of how this thinking has changed, it used to be that companies like Google would update their search index, the thing that you actually are using when you search for stuff on Google. They would update that maybe several times a day or every night or something like that. But wouldn't it be great if as soon as you edit a page on the internet, the change is reflected almost immediately in the search results? In other words, it's updated incrementally as things happen. You'd like your spam filter to also react very quickly to the changing dynamics of spam, or any sort of threat analysis that might require an immediate response, but be able to handle it at massive scale. So event streaming has just become increasingly important, and we need better tools for this. Spark has an event streaming model, as we'll see, that helps us do this. Spark is also, because of that sort of fine-grained composable capabilities I mentioned, it's also very good for implementing iterative algorithms, for implementing machine learning algorithms, which in fact was one of the early applications of Spark. And it even has support for graph algorithms as a separate module. So it's very nice for that. And Spark runs very nicely on a single laptop. It runs great on a small cluster, and you can scale it up to very large clusters to meet your needs. So you can prototype your applications locally, make sure they're working correctly, and then deploy them on arbitrarily large data sets, which is very handy, very convenient. So how does this interact with, say, the Typesafe Reactive Platform? Suppose that you're not a traditional Hadoop shop, but instead that you're building reactive applications that maybe have a play front end for serving web requests or other web services. Maybe you're using Akka in your middleware tier to handle scalable eventing and so forth. Maybe it's getting events from message queues or other sources using the new reactive streams model. Maybe all of these things are interacting with databases as needed. But now you have all this working, but you'd really like to do some data analytics, and you don't actually want to build out a Hadoop cluster to do it. You want to be able to do something that fits within your current deployment environment. Well, Spark is a great adjunct for this. We'll dive into the details a little bit here, but we could be streaming events to Spark so we can do some more sophisticated analytics than we want to embed in our Akka application. And it could be writing results or reading results to a file system or whatever, or back to a database. So we see Spark as just a natural extension of our existing platform with Akka and Play and Slick and other tools. And how you deploy this, there's a lot of flexibility here. One way you can run Spark clusters is on top of Mesos, and you might do that with your Akka and Play deployments as well. And Mesos can sit on top of bare hardware or perhaps some sort of service provider like Amazon Cloud or something like that. So you've got a lot of options now that just weren't really that easy to use with just a Hadoop cluster. Now, if you're at the scale where you really do have Hadoop-sized data, then this will naturally scale up to that because your Spark jobs will then be running in a cluster perhaps in Hadoop and talking to the Hadoop file system more than anything else. But when you're smaller scale, when you're prototyping the system, when you have a more focused service, wouldn't it be great if you can mix in machine learning or graph traversal algorithms as part of this application that you're building without having to make a big leap into a big cluster? So let's dive into these details a little bit. How would, say, Akka and Spark interact? Well, one of the things that we're building now is this so-called reactive stream model, which is essentially a back pressure mechanism with, it sort of combines push and pull semantics. So, for example, you might have an event source that's not really pushing you too hard. The producer isn't producing that many events, and hence Akka is just reading them as they come in. So it's essentially a push model. But if things get to the point of extremity where you're actually getting too many events coming in than your consumers can handle, then the reactive stream model gives you a back pressure feature that you can control the rate. You can dial it back with back pressure to ensure that you're not either overflowing your queues that are in the middle here, or you're properly at a strategic level deciding how to deal with this traffic flow. You don't want to have unbounded queues in the middle because inevitably some scenario, some spike in traffic will arise where you end up running out of memory. At the same time, you don't want to just arbitrarily drop events somewhere in the middle because you haven't accounted for it. So the idea with reactive streams really is that it gives you a strategic tool for deciding how you're going to manage the flow of events. And Okta can help you do that. It can be the buffer between your Spark streaming analysis app and the rest of the world managing that flow of events. But as events pass through, Okta might be doing some filtering, merging streams, maybe splitting them into separate output channels, and then streaming that data to the Spark's capability for handling streaming events. And there you might be doing your incremental updates of your recommendation engine or of your spam filter or whatever. Eventually, Spark Streaming probably will also support this back pressure mechanism, but today it's not there, so you can put Okta in the middle to do that for you. Let's talk a little bit then about how Spark works. Why is it so interesting? Why does it actually seem to fix a lot of these problems with MapReduce? And then come back to how streaming fits into all this. One of the key features of Spark is that it basically shards your data into a virtualized collection over your cluster. It's called a resilient distributed data set. It's resilient in the sense that each of these shards knows how it got to where it is, so that if the machine drops, it can reconstruct that data on that, say, a new node to replace the failed node. It's distributed because it is sharded over a cluster, even though you have the illusion that you have it all in a single memory buffer, say, in a single process. But it's all over the cluster, and now I can process each of these partitions in parallel, and that gives me the scalability to do petabyte size analytics and at relatively fast speeds, as long as I can fit all this data in memory or stream it through my system. So these RDDs are kind of the core feature that makes Spark able to perform efficiently, to do intelligent caching of data, and to provide the scalability that we need. So what they did with the streaming module, where Spark was originally designed for batch mode analytics, is they did actually a rather clever thing. They just said, well, let's take slices of data, slices of events as they come in, and that granularity is up to you. Normally, it's a timestamp thing, so it might be every second I'm going to grab all the events that I got in the last second, put those in an RDD, and now I have all of the facilities for analysis of that data that I've had with RDD since several years now. Okay, so we're talking about Spark Streaming, and they use this clever trick of still reusing this RDD feature, which was originally designed for batch mode systems. But what they do is they take time slices of events as they come in. That window is configurable by you. It's typically like a second to maybe a minute, depends on how frequently you want to be able to capture these slices, how much data you're getting in, and so forth. But each of these windows will have, they're called batches, by the way. Each of them will have a variable number of events. But now that they're in an RDD, I can use all of the same facilities that we have for RDDs for filtering, mapping, and other kinds of analysis. And we also have additional window functions. So I might compute some average over the last 3 windows, let's say. And that is also configurable, as is how many windows I jump at each iteration. So I might capture the last 20 windows, do some average over that, then jump by 2s, and so forth. So all that's configurable, and it allows us to not handle individual events. This is not a system like Storm where you can react to individual events. It's not built for that. But if all you're doing is updating like machine learning algorithms or running statistics or whatever, usually a granularity of a few seconds is perfectly fine, and this is what you can do with this system. So let's talk a little bit about the synergy between Scala and Spark. In fact, Spark is implemented in Scala, And a lot of people have asked Matej Zaharia, who created Spark, why he chose Scala. And I'll just read you this quote, if I may. Quite a few people asked this question, and the answer is pretty simple. When we started Spark, we had two goals. We wanted to work with a Hadoop ecosystem, which is JVM-based, and we wanted a concise programming interface similar to Microsoft's Dryad Link, the first language integrated big data framework I know of. And it continues on the next slide. On the JVM, the only language that would offer that kind of API was Scala, due to its ability to capture functions and ship them across the network. Scala's static typing also made it much easier to control performance compared to, say, JSON or Groovy. So that's why Matej chose Scala, and that's why it's such a nice fit for those of us that are already using Scala with Akka and Play to just migrate over to using Spark. So why do these things work so well? Well, it turns out functional programming, which is the inspiration for Scala, as well as object-oriented programming, is also really perfect for big data. If there's a sort of a killer app for functional programming, in my opinion, it's applying it to data problems. Because basically functional programming is inspired by mathematics, and mathematics is really all about data in the end. And FP just gives us powerful tools for working with data. And we're going to see some examples in just a second. And some of those examples are actually these little composable, reusable data operations that I've alluded to already, like being able to map over a set of values and transform them in some way, to filter out for just the things I want. Flat map is an extension of mapping. Folding would be like, the analog would be like summing up a list of integers where I'm folding them together. You can think of it that way. And then our familiar friend group by from SQL queries, where I want to bring together everything that matches a certain criteria, like say by some key or whatever. And with these little building blocks, we can compose remarkably complex data flows with relatively little code. And just to prove the point, we're going to go through an example here in just a moment. But the last point I want to make from functional programming is that it does emphasize working with immutable data, being very principled about when we do mutation of state and trying to avoid side effects in our functions. By that, I mean that I pass a value or a set of values into a function. It does its work and returns the results, but it doesn't modify the rest of the world in any way. And these characteristics have been proven to really reduce the errors in code, to make it more robust, and they make it easier for us to understand, test, and adapt this code. So it's a huge win on the productivity front too. So let's finish with an example of a common algorithm that you see in big data problems. It's really the hello world of big data. Word count is an algorithm that's very easy to understand, so you can focus on the API you're trying to learn. And what I want to show you is that whether you write this in the Scala Collections API for some small data set that fits in memory, or you use Spark to write it over a massive data set, you're actually writing literally exactly the same code, except for the setup and tear down sort of logic that's required. But let's walk through this for just a second. If you're not a programmer, I'm just going to hit the gist of the details, but I just want to give you a flavor for what's possible here. So this is what it looks like if I write this algorithm in the Scala Collections API. I guess I didn't describe the algorithm, so let me start by that. First, word count is all about reading in a corpus of documents, and because I might have many, many documents, I can read them all in parallel across my cluster. I'm going to tokenize it into a set of words, this whole corpus, and then I want to count the occurrences of all the words that I found. So for example, words like the and he and this and English are going to show up quite a lot, and I might throw those away. But what I'm really interested usually is what is sort of the general theme of this text, of this corpus? What are people talking about, and so forth. And extensions of this algorithm are actually used for search engines, for spelling checkers, and so forth. Okay, so in the Scala case, we're going to actually use Java I/O just to print out the result. That's why I'm importing it. But really this long expression is just one long expression with a sequence of function calls that are going to take the input data that I'm going to read, get each line map over each line and convert it to lowercase. I'm doing that, of course, so that a word that happens to be at the beginning of a sentence and is capitalized is not seen as unique with an identical word that's actually not capitalized. And then we're going to split each line into words. That's what this flat map line does. Then we're going to group over those words. So this is what brings all occurrences of a given word together. And then the final result is to take each word and group pair and output the word and the size of the group, and that gives me the count. And then the last two lines just do the printouts to some file. This is all it is. It's very simple. If you know the Scala API, this is really easy to follow. If you don't, it's not that hard to learn it. But the point is, when I go to the Spark API, you'll see that these lines that are highlighted in red here are exactly the same. So let's look at the Spark version. Like I said, there's a little bit different setup. Spark uses something called the Spark context, which drives everything that happens. But basically, it's really identical. I'm just going to jump right to what's the same. There it is, exactly the same lines of code that we just saw. The stuff on the outside handles input and output, but it's the same logic. So once I understand how to write Scala collection code, I can very quickly adapt that to writing big data code in Spark. Now, I should mention as a footnote that the algorithms, the particular functions I chose are not necessarily the most efficient for this problem. All of these toolkits are pragmatic in the sense that they'll add specialized functions for more efficient calculations, like this group by happens to be very expensive, and there's a more efficient way to do it. But I think the point is that you could certainly start with a less efficient model, get the work done, get it running, and then optimize later, and you have those facilities available to you. So to kind of bring this to a close then, we see a really natural synergy between the Typesafe Reactive Platform with Akka and Play and Scala, Slick, and other related tools, and this big data capability through Spark. But big data doesn't necessarily mean anymore actually massive data sets. It really means the flexibility to handle all kinds of data, to handle all kinds of query scenarios and non-query scenarios like building up machine learning algorithms and so forth. And we think that there's a natural synergy between these tools where you can take your existing Typesafe Reactive Platform applications and add data analytics running in your same cluster, or when you get to the scale that you need it, you can connect to a Spark application running on Hadoop clusters. Not only the streaming part, but you could also run batch mode Spark jobs to do other things like larger scale analytics, cleaning data, extract, transform, and load, all of that stuff. So it's like your one tool to do all kinds of things if you're a developer. And there's even add-on tools like a so-called Spark SQL library that gives you SQL semantics over structured data that integrates with tools like Hive in MapReduce, in Hadoop, if you know that tool for writing SQL queries on top of flat files. You can do things like use the GraphX library for graph computations. You can use their MLlib library and some other ones that are coming online for doing machine learning. And we just talked about the streaming capability as well as the batch mode capability. So we see this as a real win for our existing customers using the Typesafe Reactive Platform. And if you want to learn more, this talk is actually based on a white paper that will be available on this typesafe.com/reactive-big-data page on our website. And also check out my Spark workshop. It's part of our Activator program. Here's the link to it. It gives you a self-guided tutorial for running Spark on your laptop and actually working through some exercises. So check that out. And that's all I have, and I'll pass the baton back over to Laura.
All right, thanks, Dean. That was great. I just sent a link out, everyone, in the chat box to the white paper if you'd like to download that and read through it as well. You can also check out some Activator templates on our Activator page that are Spark related as well. So recommend those. All right, Dean, let's head over into the Q&A session. A couple questions have come in so far. So what is the event source doing with the additional events when a back pressure feedback is sent?
So that's a really good question. I mentioned this idea that reactive streams gives you a strategic model for dealing with a very large flow of events from producers that can't be handled by the number of consumers. Really the point is that you're going to have to decide what to do somewhere, but it gives you the flexibility of deciding where's the best place to handle the problem. It could be that in the Akka case, for example, it might be that you're managing apps. Your supervisors might decide that they're going to spin up more consumers to handle the extra data. If you have something like a highly durable queue like Kafka that's actually the source of all these events, you might just let Kafka build up the data and do what it does to scale the storage until you can drain that queue. But you may decide at some point that there's a place where you just have to drop the data. Even though that's usually not a good idea, that might be in some cases, in some applications, you don't actually need every single event, just as long as you're getting most of them. So yes, it's a really good question, but what it does is it gives you a way of strategically deciding where to handle this problem, not just by default, either running out of memory or just dropping them somewhere that maybe isn't the right place.
Got it. Okay, thanks, Dean. Next question, do you expect that there will be a convergence of Spark streaming and reactive streams?
I think so. I think there has been some discussion of using reactive streams. I should say that reactive streams, or in particular the Akka stream implementation, is still a pre-release work in progress. But I believe the Spark team is interested in possibly integrating it because I've already seen discussions on the mailing list about the need to have more resilient capability for dealing with streaming events. Right now, Spark streaming can listen on a socket, for example, but it doesn't give you the facilities for controlling like back pressure or handling dropped events or whatever. One more question, I'll take that. It's how does Spark work with GPU clusters? That's a really interesting question. I think that I'm not aware of any work that's been done to incorporate GPU processing with Spark. That's actually an interesting problem to me. It should be feasible to integrate a module into Spark that delegates some computation to GPUs, but I'm not aware of any system that does that yet.
Okay. Yeah, sorry about that, Dean. I was on mute before. Just a final question here. Are there any interesting projects out there to help you optimize Spark queries that you know of?
That's a good question. I don't actually know of any myself. There's certainly a growing body of wisdom about what to do. I think that's probably an area where we're going to see a lot of maybe innovation is the wrong word, but in other words, the Spark team is probably going to have to provide you better feedback for people to know how to tune queries and better guidance about how to make them work efficiently. So there are some things that are already known about efficient use of Spark. I glossed over a lot of the details, but one of the things I was doing in that example was passing little anonymous functions to these combinators, the so-called map, filter, and so forth. And there are ways that you have to be careful about how those are written so you don't end up trying to send too much information over the network as that code is distributed around the cluster. But yeah, there's a bunch of things that we need better visibility on. The next?
Okay. Sorry, Dean, so there was just another question that came through. What exactly does .cache do in Spark?
Oh, yes. So that's an interesting feature of Spark, actually. So if you know that you've got an RDD in memory, so suppose you've gone through some transformations, and each one creates a new resilient distributed data set, RDD. And suppose you've gotten to a point that you know that you're going to be continually revisiting this particular RDD to ask queries of it. Maybe you're in the interactive shell, or you're just going to keep passing over the same data. What that .cache function does for you is it tells Spark, make sure you cache this data in memory because I'm going to be visiting it a lot, rather than say flush it to disk once other things come into scope. So that's the purpose of it. It's a hint to the cache to save data that you know you care about.
Cool. And then I think we might want to finish on some questions related to Akka. So there was a question that just came through about how Spark is making use of Akka. And is Akka clustering being utilized? Is there anything you can kind of expand upon there?
Right. So they are not using Akka clustering. They use it a little bit internally. I'm not actually sure of all the details, but there has been some discussion between Typesafe and the team at Databricks, the main company behind Spark, about how they want to maybe expand their use of Akka and take advantage of some of the facilities it provides. But right now it's a fairly small usage of Akka.
Okay. And can you give any examples of some real-world companies that are using Spark? What kinds of projects might be interested in using Spark technology?
That's always an important question. You don't want to be the early adopter that finds all the problems. I believe that there's a big team at Yahoo that is using Spark. There's another, I can't remember who it is. There's another company in the Valley that's actually contributing back a number of tools to Spark, but I honestly don't remember who that is. Certainly the adoption is not yet as big as MapReduce. It's not as big as the Typesafe Reactive Platform, but I went to the Spark Summit with over 1,000 people, I think it was, just a month or so ago. There are a lot of people who are starting to use it, a lot of companies that have used it successfully. Probably the best thing to do is to go to the Spark website. It's spark.apache.org, and I think they do have a users list, a so-called Powered by Spark kind of page, if I recall correctly.
Yeah, one of the attendees just pointed out that DataStax is contributing and using Spark as well. So I think if you go to the Databricks website, you kind of learn more about the different companies using. Okay, well that about wraps up the Q&A session. Dean, is there anything else that you'd like to close on? Or again, I do recommend people checking out the white paper if you get a chance, so you can find that URL either in the chat box or on our website. If you go to the platform overview page and then to a section about big data, you can find it there.
Yeah, so please check out those resources, and I'd love to hear from you about how you're using Spark, how you want to use it, how you use it with the Typesafe Reactive Platform, any of that stuff. Please reach out. I'd love to hear your stories.
All right. Great, Dean. Well, thanks so much for presenting today. This was awesome. And if anyone has any questions, as you mentioned, just feel free to reach out for us and look for the recording shortly. And we hope to see you on future webinars.
All right. Thanks, everyone.
Thanks.